Good morning, everybody. Let's give it another minute for more people to join, and then we'll begin. Okay, let's get started. Let me just confirm that you can hear me. I wasn't talking before. All good, okay. All right, everybody. Welcome back to System Software. Before I begin today's lecture, let's go over a couple of things from the last few lectures. I'm glad to see that most people have Git and Vagrant set up. I think most people have that. If you still are having trouble with either of these, please come to office hours today or ask in lab. I've gotten some questions about problems with logging into Zoom. Viewing the screen recordings. One thing to make sure of is that when you're logging in to Zoom, that you use this SSO option to log in. Even if you've signed up with a UCF email address, you need to use the UCF organization account. And apparently this is already set up for you. If you click on this SSO option, either in the mobile app or on the web or in the desktop client, it should take you to a UCF authentication page. Then you should be able to access the Zoom recordings. I've heard from students that they are able to access the recordings. So students should be able to access the recordings via web courses here by clicking on Zoom and cloud recordings. And you should be able to access these. Does anyone still have problems accessing the cloud recordings with Zoom? If you do, then try that. Make sure you're logged in with SSO. You may have to log out of Zoom if you're logged into another account. So I'm looking at the chat. So if anybody has questions or issues, let me know. Okay. Oh, one thing I want to also clarify is the role of labs. So I know labs can sometimes seem unclear what the use is. So I was talking with Josh about this. Also, somebody asked, should we always have Vagrant ready for class? For today, for classes where we do live coding, you should have Vagrant ready. Today is going to be very programming heavy, so it'll be useful for today. It just depends on the content of the class. For most of the classes, I'm going to do a little bit of live coding for the projects. But you can always go back and watch the recording if you don't have Vagrant ready. So let's talk about labs a little bit. As we saw last time and the last couple of times, even with this 3-hour block, there's a lot of content to go through. And so the labs are going to be able to go into more detail and answer questions that you have about concepts and stuff that I may have to go over fairly quickly during lecture. So labs are going to be really important for that purpose. There's also going to be some additional content that we don't have time to go over in lecture that will be useful, particularly for doing the project. As we'll see today, I'll point out where the labs will go into more detail today, particularly when specifying the syntax of languages, which we'll see today when we do our toy compiler. And it'll just give you a review and give you extra time to ask questions, kind of like office hours, but in a group setting. So that's the role of labs, and today is going to be very useful because we're going to be doing a ton of live coding in class, and it's going to go by pretty fast. I'm expecting that you can rewatch this lecture to be able to complete the homework assignment for today. But yeah, so if you see me kind of going pretty quickly or coding something, you don't completely understand something, can certainly take questions during class, but labs are really a place to do recitation and review and be able to ask even more in-depth questions. Okay, last time we went over system tools. We had a pretty fast command line crash course. Went into a lot more than I expected to. Didn't even get to cover some of the stuff on Makefiles and separate compilation. We're going to cover that today when we do our programming assignment. But are there any, so nobody came to office hours Tuesday that I saw. So I either students couldn't come to that time or there weren't that many questions. Okay, so one question here is, I found online that oftentimes the newer compilers won't generate assembly code unless specified. It depends on what we mean by assembly code. So if by assembly code we mean the text format that describes machine code, then there's no reason for compilers to ever generate the text form of that. But if by assembly code we mean machine code, then compilers are always generating machine code. So when I say GCC-S, I'm telling the compiler to stop when generating assembly, don't do linking, but also give me the text of the assembly file that it generated. So it's almost like just a difference in representation. But technically assembly is like the text form of assembly. And there may be some version of this in memory that the compiler is generating. Does that make sense for the person who asked this? It's just more about defaults. The default is to just generate a binary. Okay, so if there's no other questions about system tools from last time, rewatch. It's more about practice. just practice using the command line. And we're going to get more practice today. And I'll try to review what you have to do in order to submit your project, to build, to run it. But really practice exploring the file system through Bash, through the command line. Okay, let's go to our next lecture, Writing a Toy Compiler, which you can find from the website. Clicking on lectures, and the notes are up already. Oh, well, okay, so one belated question about the system tool. The reason for this, as I hinted at last time, was that, in my opinion, great programmers know their tools, and your computing environment is really your main tool when doing programming. And knowing the command line exposes you to many more tools that aren't available to you necessarily from a graphical interface. And they basically allow you to do computer operations programmatically. You can write scripts to do all kinds of file system and programming environment setup that you may have to find some specialized graphical application to do for you if it exists at all. Okay, let's get into writing our own compiler. So the purpose of this class is to give a very simple introduction to writing a compiler with a very, very basic language. And this is going to show that even though we have a very simple language, it's not trivial to write a complete compiler for it. But the language is small enough that I hope we can finish writing it together in class today. Now, I'm going to go a little fast because there is quite a bit to cover, but you should be able to go back to the recording and hand write this compiler yourself. Where am I? Okay, so I'll talk about the assignment in a second, in a couple slides. But let's go step back a little bit and look again at what a compiler is from, you know, a 10,000 foot view. What do we mean by a compiler? Okay, so a compiler is
Professor, your mic is muted, by the way. Professor.
Thank you. I was just talking to myself for a little bit. So yeah, sorry about that. I'm glad. So it seems like most people are still here. Something I don't know what happened with my machine. I had to restart it, and well, yeah. Hopefully that won't be an issue. Of course, you know, Murphy's Law. Okay. Let's go back to our slides here. And what I was trying to say, let me just get my whiteboard up again. All right, so just a quick, oh, that's crashing. All right, so I think because the Zoom talk stopped, there's going to be multiple recordings. There's going to be 2 recordings for today's lecture. Just be aware of that in the recordings. Just look at the timestamps. All right, so what I was trying to go over before this unexpected break was just a high-level view of a compiler. We looked at this a couple weeks ago, but basically the compiler is a program that special program that takes another program as its input in some language and produces an equivalent program as its output in usually machine code or something usually that's a lower level or closer to the physical hardware than the input language. And then that program itself has an input and an output. But of course, as we saw a couple weeks ago, the compiler itself is a program. And if we write that in a high-level language like C, then we need a compiler in order to compile the compiler. And so today we're going to go into how the actual internals of the compiler are structured in general, and then we're going to write one together for a simple language. So someone asked, does it take the compiler, I presume, does it take the program as assembly or a different language? The compiler takes some other language, some language that is not executable on a machine, and produces assembly language. So if you had assembly language already, you could use your assembler to create machine code out of it. Assembly isn't strictly machine code, but it's much closer. It's very close. All right, let's get back. And yeah, just one thing I wanted to say is that the kind of purpose of the compiler is very much a human one. We can take a language that's much more comfortable and more natural for a human to write. I mean, you could argue that programming is not all that natural to do. We still have a lot to learn, but it's usually can be easier than writing in machine code. I mean, it's definitely easier than writing in actual machine code, entering the numeric operation codes and everything. So in some sense, it bridges these human-friendly languages like C. I know you may be laughing and wonder, at me calling C a human-friendly language, but compared to writing in machine code in binary, it's much more human-friendly. And so today we're going to write a compiler that just takes some very simple binary arithmetic operations, addition, subtraction, etc., and produces assembly that can be assembled and run on an Intel device. And it's also just going to print the result of each operation. So for example, our programs are going to look like this, where we have some single-digit numbers, one operator, no parentheses, no nested stuff. followed by a single semicolon. And the assembly that we're going to get out is going to look something like this. I didn't include the code for printing it, but we'll look at that later. But this is roughly what we're going to get. If you haven't seen Intel assembly before, but I assume everyone's seen MIPS from CDA, from the computer organization class. All this is saying is put the number 1 into the A register, put the number 5 into the B register, add them and store the result in the A register. And similarly for subtraction, move the number 7 or the immediate 7, that's what the money sign indicates. This is AT&T syntax. We'll talk more about the different syntaxes for assembly, but this is what GCC outputs by default. So it moves the immediate constant 7 into the EAX register or the A register, moves the number 4 into the B register, and performs the subtraction, subtracting B from A and storing the result in A. Now, knowing what this means, knowing what the ISA, the instruction set architecture of the machine you're working with. Now, I am no expert in assembly, so we'll just use reference manuals, and I'll just give you the exact assembly instructions you need for your compiler. So somebody asked, is this class heavy on concepts from computer organization from CDA? To write a compiler, you have to, if you want to write a compiler for a machine, you have to understand enough about how to write assembly in that machine. But you don't have to be an expert on the actual underlying architecture of the machine, unless you want to do some aggressive optimizations. Knowing the machine from the ISA point of view is enough. And we're only going to go into the computer, the low-level aspects of the computer, just enough so we can write a compiler for it. So I know that's kind of a general answer, but it's, this is not a repeat of CDA. I just expect you to have some understanding of assembly language, of some assembly language. Okay, so I'd like to hear from you for a little bit. So how would you write this? So this is the assignment, and you've got to take this input program, whatever this means, and produce this output program. So how would you do it? So somebody said switch statements. Okay, if statements and printf. Okay, so that's the kind of control flow. Okay, so somebody's starting to get a little to the nitty-gritty of what it really does take to write a piece of software like this. So somebody said go character by character, then run the commands. Okay, so remember, this is the output program, nothing's being run. But this brings up a good point about going character by character, because it sort of begs the question, what is this input program? How is it represented? Somebody said start with opening a file. That's a really good point. So again, this gets into how the machine represents the input and output. Okay, what about knowing the difference between, say, plus and minus? So some people hinted at this with switch statements and if statements. Some are saying map operators to certain strings. Okay, yeah. So I think you guys have a pretty good sense about roughly how you would do this. Yeah. So I think you all have a good sense of this. And in this class, we're gonna formalize some of these concepts of what it means to scan each line, what it means to look character by character. And this is where I talked about a couple weeks ago about having some computational theory. This is where some different models of computation make it really much easier to reason about these notions of how do we scan character by character and find the words we want in the language? And how do we look line by line, or in the case of a language, how do we look construct by construct to map those constructs to some assembly code? So line by line makes sense for this language, but remember, if you're in C, you've got all of this nested structure. You have these if statements nested inside each other, and they can be arbitrarily nested. And so we'll look at some models of computation. And somebody mentioned a stack and a prefix assignment. Yeah, this is very much related. So this is really about language processing. And stacks, we're going to be looking at stacks for sure. Okay, so the assignment today is really not about writing a compiler yourself. We're going to write the compiler together, and I'm going to implement it. So the objective here is not to write your own code for this. What this is really going to be testing is using the tooling that we went over last time. So you're going to practice using the compiler on the command line, building and running software on the command line, and also practice submitting the code through Git. So what that means is you're just going to follow along with the implementation that I do in class so that you can see a little bit of this compiler design firsthand. It's really hard to both learn new tooling and also have to write code. So it frees you from having to do that. And what I mean by follow along means you type it out by hand yourself without help from others. So if somebody else typed it out by hand and you say, hey, I'm too lazy to write this out, can you just send it to me and I copy it? That's cheating. So that violates academic integrity. I really want you to type this out by hand yourself. It's only a couple hundred lines. It's not that long of a compiler, not that long to code. And you can just look at my code and write it out by hand. But I really, really want you to be able to write it out by hand yourself and go through the command line to compile and run this stuff. Because if you just copy it and then we get to the real project, when you have to both use all of the system tools that we're using in this class and have to get the algorithms right and do debugging, it's going to be a mess. It's going to be much, much harder. So take this opportunity as a fairly easy assignment to just hand copy code. And the reason that I'm having you do this, it might seem a little bit like busy work, but I can tell you that when I learn programming languages or even learn a new keyboard, or I'm learning new software or new techniques, I will just hand write code. If I have to learn a new language, I'll find online examples and just hand write it. Because it may feel like busy work, it may feel not useful, but it turns out that you can kind of gain a skill in coding and gain some muscle memory that'll make you really, really fast when you do coding later. So as I just want to point out, this is the only time when you're allowed to actually use someone else's code, because you're using my code. This is code that's going to be publicly available for everybody. So somebody asked, it's like writing out notes by hand versus typing notes. I don't know. I mean, we're going to be typing the code. I don't know if that makes a difference. But it's more like doing it versus seeing it. It's giving you some it's giving you some muscle memory in typing code. So somebody says they hear writing notes by hand help you memorize info better. Maybe. Yeah, I don't know. Okay, so as I said many, many times, I showed the diagram already. The input is a program in our source language, and the output is an equivalent program in the target language. So the compiler is not running the program and giving you the output. That's an interpreter. Compiler is just taking basically a text file as input and a text file or an object file as output. And both of those things are programs. The output of the compiler should be able to execute on the machine, and the input is the language that we have created and that our compiler is implementing. So let's go through some of the internals of how compilers are structured. This is a diagram from the Dragon Book. And so somebody asked an interesting question, but I'll get to that in a second. So here's the phases that really any modern compiler goes through. We've got the lexical analysis, syntax analysis, semantic analysis, intermediate code generation, optimization, and code generation. Actually, I don't know the page. it's early in the book. I'll give readings for the Dragon book at the end of this lecture. All right, so for lexical analysis, think. Let me see if I put. Yeah, I'll reiterate this a couple of times, but for lexical analysis, think identifying words in the input language. If the input program is in a language, think of lexical analysis. So what is it called? So lexical has to do with, I mean, it comes from the Latin word for reading, but you can think of it as like a dictionary of words. So the Lexer is identifying the words of the language. And so as somebody pointed out before, that you would scan character by character to identify the input language. Yeah, from the input language. Here we've got a sequence of characters for some assignment statement here, getting turned into a set of lexemes and tokens. So tokens are just groups of characters. And so here you can see that it's turning it into an identifier, an equal sign, another identifier, a plus sign, another identifier, a multiplication sign, and a number. So that's what the Lexer does. It's just like when you break apart a piece of text by spaces, so you tokenize the input. That's a simple kind of lexing. If you just assume that each word is being separated by white space, then tokenizing the input is a kind of lexing. But as you can imagine, for an input language, it's not enough just to separate things by space. In C, for instance, you don't have to put spaces between arithmetic expressions. And so identifying what the words are in the language is a little bit more complicated than just, well, let me break things apart by spacing. And we'll go into some of the theory behind that in a couple of weeks. Okay, so that's lexical analysis. Lexical analysis is taking a stream of characters from the input and breaking it up into individual words or lexemes in that language. The syntax analyzer takes that sequence of tokens and determines the hierarchical syntax of the language. Just like in English, where you have this hierarchical syntax, you've got sentences and then noun phrases and verb phrases, and a noun phrase might have articles and adjectives. The syntax analyzer does this for our input programming language. And so just like a human language, the input language can have a grammar to define this hierarchical syntax. The syntax analyzer takes this sequence of tokens, which is just a list or a sequence of tokens, and turns it into a tree. It's basically doing sentence diagramming. And so now we have this tree structure, and in this case, we even have the order of operations encoded in this tree structure. Just like someone mentioned that prefix to postfix exercise or that prefix evaluation exercise, using a stack. And so we'll get into this when we actually do coding, but there's this equivalence between using a stack, traversing a tree, and recursion, that they're really all describing the same kind of computation. So in the same way that you use a stack to do this prefix expression evaluation, if we imagine doing a tree traversal on this tree, and if we did a post-order tree traversal, the first operation that we'd hit is this multiplication. So even though there's nothing about order of operations in a sequence of tokens, so I mean, there's no meaning at all to this multiplication sign, by turning it into this tree structure, if we enforce this grammar on the input language, the tree structure captures this order of operations. And when you write that prefix evaluator using a stack, and if you traverse this tree, both of those are actually using a stack to keep track of the previous nodes, the nodes that are pending. And the first node that you process is the multiplication node. And so hopefully you can start to see a little bit of this connection between recursion, tree traversal, and stacks. Yeah, so somebody pointed out that you would think you would need parentheses to do this. But actually you don't. For order of operations can be encoded in the syntax of the language. And then when you go to actually implement, evaluate, or translate that, the order of operations is already described by the syntax of the language. And you can just do a simple tree traversal, not even worrying about parentheses, not even worrying about a stack, because tree traversal is done recursively. And as we'll see when we actually implement functions, recursion is possible because of a stack under the hood. Okay, great. So I think some people are making some connections here. Then we've got semantic analysis. Semantic analysis is basically type checking in most languages. So for instance, here, the type checker will have an axiom or an assumption that says, okay, if I see the text of a number, then that means that this 60 must be an integer. If we know that multiplication must be an integer, then we have to show that then in order for this operation to work, this identifier also must be declared as an integer. And we'll go into that in about a month. We'll go into the details of type checking. But basically, once we have this tree structure, we can use a type checking algorithm to iterate over that structure and basically prove that the program is using types correctly. And that will actually guarantee that certain runtime errors are not possible. So somebody asked about calculators. So some people are saying calculators can't do order of operations. So if we're thinking about a desktop calculator, the reason for that is the desktop calculator doesn't actually have an input language. Well, in some sense, or at least the language is restricted to just doing a single operation at a time, kind of like assembly language. Order of operations, or trying to design a language that has order of operations, really gets into compilers. It's really about language design. So a calculator that does support order of operations is one in which they've actually implemented a language that you can write those expressions in. So it's really the difference between the physical instructions that the machine supports and some language that a language designer or compiler writer invented and wrote a program to process for you. Okay, so once we have this tree, it's nicely type checked. We've got the tree representation of the language. Then we can generate intermediate code. And so I'll show a diagram later about why we would want to generate this intermediate code instead of directly generating machine code. But just for now, realize that most modern compilers don't generate assembly code right away. They generate an assembly-like code, a language that's, it depends on, there's a lot of design and engineering choices that go into the intermediate language. But basically all of them are gonna be something in between machine code and the input language. Then we'll do optimization. So yeah, one of the reasons for having intermediate code is to have language independent optimizations. So then we'll do optimizations, which I'll show an example of. And then finally, we'll generate machine code specific to that machine. So questions at all on this diagram? This is all maybe just new material for everybody. But any kind of clarifications? Okay, so I talked about lexing and parsing and type checking. So let me show, here's a diagram of the Llvm compiler infrastructure, which is an industrial strength and very common compiler framework. And we see here on the left, these are the input languages that the compiler supports. And the right-hand side has the output languages, the output machines that it supports. And so somebody asked, language specific, does that mean the first 4 steps we can recycle for basically any language? So actually it's the other way around. If we have this front end, the first couple of steps, lexing, parsing, type checking, if we have that written for C++, and we, instead of generating assembly code, we generate this intermediate code. This IR stands for intermediate code. Then, and we already have a generator from that intermediate code to say Intel x86. Then if we want to implement a new language like Objective-C, we can compile that language into our intermediate representation, and then we get the backend code generation for free. And so why is that easier? Because the intermediate language has less of the specifics of the machine code built into it. It's almost like a high-level assembly. So in Llvm, for instance, there's infinite registers. There are function definitions in this IR. And so it's much easier to compile to that language than it is to compile to Intel or ARM. And moreover, if we were to write, so there's 5 input languages, or yeah, 5 input, can I count? 5 input languages and 5 output languages here. So if we had to write a compiler for each of those combinations, we'd have 25 compilers we'd have to write. By having this shared infrastructure, then there's only 5 front ends and 5 back ends we need to write. Moreover, we can make some of the optimizations independent of the input and output language and just make them on the intermediate representation. So yeah, so somebody asked if the IR is a liaison for the input and the input language and the backend. And yeah, that's basically right. So somebody asked, so you couldn't compile Java into something like C and then use the C compiler. So this is, I think, nowadays called transpiling. But you could certainly, compile Java into C. You could do that. You can really compile any language. You can really translate any language into any language, as long as you have libraries to support what that, yeah, transpiling is a strange word. Not a huge fan of it. It's really code transformation. I mean, code transformation is kind of the general term for taking some piece of input code and translating it to another piece of input code. I mean, this is all just terminology. But actually, so to the point of, so I don't know of any Java to C compilers, but I can't imagine why you wouldn't be able to do that. But originally, the original C++ compiler actually generated C code and not machine code, because C already existed, and C basically acted as an intermediate language for that compiler. So somebody asked, aren't there languages that will simultaneously make something compatible with Apple and Android? So yeah, once you have an input language, you can write a compiler that retargets multiple backends. And those backends don't necessarily have to be machine code. They could also just be other programming languages. So for instance, C++ could generate both C and maybe Objective-C. You might even be able to target Python. So some of it, so from the language specification point of view, you can definitely do that theoretically, but there's a lot of runtime libraries and runtime behavior that you'd have to emulate basically in your target language. Okay, so I think that's enough on the structure of compilers. We'll talk about optimization later, but basically, here's an example of constant propagation, where, as you can all kind of go over this yourself to sort of convince yourself this is true. But this compiler here, the compiler can basically avoid any variables here and just replace y with 11. Because for every execution of this program, y is always 11. And compilers can do this. And compilers can do really, really sophisticated optimizations for you. But we'll talk about that near the end of the semester. Okay. All right, I think we got plenty of time to do this. I hope we have time to do this. So let's write a toy compiler together. So as I pointed out, it takes a list of binary arithmetic operations, produces Intel assembly, and then we can use GCC to assemble and link that into an executable. So here is a more complete output. This is the same as the example that I showed before, where we just do an arithmetic operation in assembly. This mess of code here, don't worry about the details of it, but this is how you would call the printf function in assembly. So we'll talk more about the details of this later, but we'll just basically use this as a template. If we have the thing we want to print in EAX, this is how we print it. Now the actual string, the format string, we'll go into details of this later. So the output will be assembly code, that is a text file describing machine code. And by convention, GCC uses the .s extension. So somebody asked if this is going to be related to the official compiler assignment. The actual code itself will not be reused for it, but the style of coding and the way you build and run the compiler will be virtually the same, will be very, very similar. So the whole point of this is that I can give you a little heads up on writing this compiler, because I'm going to give you templates for the compiler. And so this will help you see internally how the compiler I'm giving you the design works. Okay, so in order to actually write this compiler, we need some specification. What do we mean by the input language, and what do we mean by the input language, and how should that be mapped to our assembly language? All right, so what do we really mean by arithmetic expressions? So as I hinted at last time, so let me go over to my Vagrant machine here. Oh, my Vagrant machine is not up yet. So while that starts, let's just go over to the Scratch folder here. Okay, so if we've got, well, actually, let me go to the toy compiler. So here's our, here's our example program here. And remember, even though this looks like numbers on the screen, we went into this whole discussion last time about how this is really just numeric codes that by convention, all of our system tools, our editors, our console, when it sees that, it writes out a shape that we recognize as an Arabic numeral. And we can reveal that using this OD command, this octal dump command. And so if I dump this in hex, then there's a little bit of an issue with endianness here. But these reveal in hex the numeric representation of this text file. To make this a little easier to read, we can dump this out in C format, dump this out in a C format style, and see that even though it says 1 here, this is going to be actually represented in the machine using some numeric representation. Because remember, the processor and the machine are just, you know, a sequence of wires that have voltages, high or low voltages, and 16 bits means you have 16 wires going into your processor. And we refer to those combinations of voltages on the wire using binary numbers. And if we want to do processing of text, then we need to represent that text numerically, or at least represent that text using high and low voltages on wires. And by convention, we use this ASCII code. There are other conventions for representing text. There's Unicode, there's Ipsodic, the IBM version. But for this class, we're going to be using ASCII. So what we really mean by an arithmetic expression is, first of all, numbers are a number represented in ASCII code, because all of our system tools, all of our editors understand that convention. And when we type on the keyboard, that character code is what's being stored in the file that we save. So that's what we really mean by numbers. What about arithmetic operations? Well, it's the same thing. Each of these symbols for an operation has an ASCII code. So that's what we mean by numbers, and that's what we mean by operations. But what do we mean by an expression? And so we'll talk about a little bit, so when I talked about syntax, I started hinting at the fact that you could encode this order of operations in a tree structure. And when we formally describe what an expression is, we actually will describe first its syntax. Just like we describe the syntax of human language, we can describe this hierarchical syntax of the language. And that'll allow us to do whole arithmetic expressions with nesting and order of operations and parentheses. And so there's a whole bunch of other questions when it comes to lexing, like, are spaces allowed? What do we mean by a new line? So new lines are, what is it, 08, I think, 0A maybe? I don't know, I don't memorize the ASCII sequences. But in C, this is denoted by /n. So remember, this new line is just a single character. When we go to display it with an editor or a terminal, that character is interpreted as drawing the next characters on a lower, basically lower down on what we interpret as a new line. But really, when we look at the machine representation of that file, 0A in hex is the code for that character. So even though this looks like a lot of space, it's really just a single character. Similarly with tab, this is the case. So if I have well, it'll be hard to see, but I'm hitting tab here a bunch of times. But you can see that 09 is the tab character here. Yeah, anyway, so tab looks like lots of spaces, but it's really just a single character. So somebody pointed out that the null terminator is also a single character. That's right. So semicolon. So somebody is not seeing semicolon. So I'm just going to go to the ASCII table here because I don't know these off the top of my head. More at ASCIItable.com. So let's look for semicolon here. So it is hex 3B for semicolon. And we can see 3B here and here. Okay, so same thing with semicolon. What do we mean by semicolon? What is it? What is it for our compiler? All right, let's get back to this. And how do we represent arithmetic operations on the physical machine? How do we represent numbers? We can use assembly to do this. So the machine does have its own binary coding for all of this stuff. So numbers, at least unsigned numbers, have the basically are in straight binary. For unsigned numbers, we have this 2's complement representation. For arithmetic operations, we have opcodes to tell the machine what operation we want to run. But this is all CDA stuff. So this is where, you know, the kind of CDA stuff ends and compilers start. Because we're just compiling to assembly, the assembly language, the assembler will handle all of those details for us, like the physical representation on the machine, the opcodes. It'll handle all that for us. So we're not going to have to worry about that stuff. All right, so I'm going to give the informal syntax and semantics of this language. And in lab today, hint, hint, go to lab, Josh is going to actually show you a formalization of the syntax so that in a couple of weeks when we look at the computational model, look at this computational model for parsing, we'll already know about the formalism that we use for syntax. So it turns out that there's this very strong connection between formal languages, even human languages, grammars and semantics, and computation. So basically, yeah, it's a pretty amazing correspondence. We'll see it in a couple of weeks, but there's this correspondence between models of computation and language. Okay, so the informal syntax of this language is a program in our toy compiler language is a list of statements. What is a list of statements? A list of statements contains a single statement and then another list of statements. That's basically just a linked list. So what is a statement? A statement contains a single expression followed by a semicolon. What's an expression? An expression contains a number and then an operator and then a number. What's a number? A number is a single ASCII code for a single digit, and an operator is also the ASCII code for plus, minus, star, or /. So this is a little bit informal, but you can see it has this kind of hierarchical structure where a program is composed of some other syntax, and each of those has their own symbols that they represent. And at the very bottom, we have basically the tokens in our language, the lexemes, or the characters. In this case, I made it simple where you don't really have to do much lexical analysis in this language. Okay, questions on this so far? This kind of informal syntax of our language? Oh yeah, so somebody pointed out that these are swapped. I think this is because of endianness in Intel, but I might be wrong. I can't remember. Okay, so let's look at the informal semantics of the language. So syntax is like a restriction on legal inputs to that language or legal utterances in the language. And the semantics is what that language means. So for our language, informally, the ASCII code for digits means machine integers. So remember, the ASCII code for the graphical representation, and the graphical representation of the number are not the number according to the machine. Each ASCII code for an operator corresponds to some machine operation. So as somebody pointed out, it's a mapping between characters in the input and machine code, and that's very, very, very close. That's a semantics of that's a kind of informal semantics of the language. And finally, each complete statement computes and prints the result of the machine operation. So that's our informal semantics. There are actually more formal ways to describe semantics as well. So we'll talk about formal ways to describe syntax. But that's the formal way. And there are also formal ways to describe the semantics of a language. So I want to point out there's kind of a cool idea here from Noam Chomsky, who kind of created modern linguistics, or at least tried to make it rigorous, to point out, kind of intuitively point out this difference between syntax and semantics, and provide a little maybe intuitive notion behind his idea that there's this kind of inbuilt ability in the brain for handling syntax. This is still kind of a controversial idea in linguistics, but in computing and cognitive science, we can actually see how computation can process language, and how there is this kind of, we can use this difference between syntax and semantics to write a compiler and to do processing of language. So, okay, so there are these two sentences that Chomsky made to point out this notion between syntax and semantics. So, okay, in the first one, we have the sentence, colorless green ideas sleep furiously. The second sentence is, furiously sleep ideas green, colorless. Now, from the audience, do you guys notice anything about these sentences? So is one of them kind of, okay, so somebody already kind of.
There's like, it's like how in French they have like the beauty, age, goodness, size adjectives. There's sort of like an implicit order where all English adjectives go. It's just,
right, so
it's a bit more complicated.
So somebody in the chat said the second one feels wrong. And as our speaker just said, in French and in English as well, there are orderings on words that we think of as right when we hear the language. And so you can actually tell with non-native English speakers, they may reverse even the order of adjectives. So like big red car versus red big car. Even down to the ordering of adjectives, there's some orderings that feel right. And this notion of feeling right is what Chomsky claims is actually this inbuilt ability to recognize syntax, and recognize syntax even independently of the meaning of the words. And so in the same way, our compiler is actually going to recognize the syntax independently of any meaning of those characters. There's this theory in linguistics is that our brains actually do this. And this is Chomsky's explanation as to why, as one commenter pointed out, the first one kind of makes sense, or at least seems correct in a sense, even if we don't know what the sentence means. And the second one just seems like completely nonsensical. And so the theoretical reason for this is that the first one is actually grammatically correct English. We have an adjective, two adjectives modifying a noun, and then we've got a noun. Oh, well, okay, it's here actually. The structure is here. So we've got a noun phrase that's composed of two adjectives and a noun. And we've got a verb phrase, which is composed of a verb and an adverb. And this is ordered in the common ordering in English for most statements, noun followed by verb. And so in languages like Latin, for instance, where instead of subject, verb, object, you've got subject, object, verb, or other languages that may have different word orderings. In those languages, the syntax that you learn kind of intuitively, you pick up as you're intuitively learning the language, you get this sense of what the syntax of the language is. And Chomsky's theory is that this is evidence that we actually have built-in, inborn ability for language and for syntax. So regardless of whether that's true or not, we can actually exploit this notion to write a compiler. get back to, okay. So I kind of went over this already, but I'll just go through this quickly, and I should get coding soon. All right, so we talked about this already. Each byte corresponds to it. So we're gonna, our Lexer is gonna take, ooh, screen delay is hefty. All right, I'll keep that in mind. I'll try not to switch back and forth too much. Okay, so our Lexer, remember our Lexer takes a sequence of characters and turns it into tokens, a sequence of tokens, or lexemes. So the tokens in our language are going to be these four. We're going to have a number, which is just a single digit, an operator, which is one of the 4 ASCII codes for the operators in our language, a semicolon, and the end token. And this is more of a, this is just going to signify that the program is finished. This is going to correspond to end of file, basically. Okay, and in order to actually, okay, so last 2 weeks ago, I talked a lot about this difference between specification and implementation, and that if you can break your problem down and get the sort of individual specifications of that problem implemented correctly, and then you can just compose them together into a correct program, rather than trying to say, well, let me just write the entire program in one implementation and then do a bunch of debugging. Instead, if we can break this problem down into smaller specifications that we can get right and are easy to get right, and we can compose them together and have much stronger guarantees that our entire application is right. So we can think of this, so yeah, I won't go back to it, but we can think of this phases of a compiler as a way to break down a compiler into individual components where the specification of them is a little bit easier. And then within those, we need to also define APIs for the individual phases of the compiler. Oh, people cannot hear. Okay. I just, fortunately, I did not curse that time. So you can't. Yeah, first time it went happened. Hopefully it wasn't recorded, but I was talking a bit like a sailor. All right. So we've got the phase of the compiler, and that's a nice convenient breakdown of the specification, which all compilers writers know. So we're going to use that, and each of the projects is going to be broken down into that. But let me show you within each phase for this compiler the API. So when I was writing the compiler, I was coming up with the API, but we're not going to go through that process. That's a little bit of a longer process. I'm just going to give you, here's the API we need for each phase of our compiler. So for tokens, there's going to be, for each one of the tokens in our language, we're going to have one function that their entire job is to just take the input, take whatever is needed to create that token, and just return a token structure. And then the Lexer is going to define this Lex function. And that Lex function is going to say, okay, you call Lex, and I'm going to give you one token from the input. So the Lexer is a nice abstraction away from all this ASCII and non-printable characters and files. So this abstracts away all that into just giving the compiler, okay, I want a sequence of tokens, and I don't want to worry about ASCII. I don't want to worry about files. That's what this Lexer does. We'll see that the other functionality that it does with matching patterns, but we'll see that in a couple weeks. And that's formalized in regular expressions and finite state automata. The parser is going to implement this syntax that we went over. Remember, we have three constructs in our language: a list of statements, a statement, an expression, and the program itself. So 4 of them. And we're going to have constructors that build each node of this tree. We'll see that in our code. And so the interface, and then it's also going to interface with the Lexer. So the parser needs to read each lexeme one at a time. So it's going to have some functions to get the next token from the input, And we'll talk about this look ahead in a second. So basically, in order to do parsing, we need to know what the next token is to make a decision about it before we actually move on to consume that token and move on to the rest of the file. We'll see that when we code. And this is formalized in context-free grammars in the language world and push-down automata in the theoretical computation world. There's a lot of fancy jargon here and a lot of math, but really it's a formalization of this notion of hierarchical syntax. And we're going to cover that, yeah, in lecture 7. We're going to cover that later. Okay, and then finally, we have the code generation step. So I'm skipping a whole bunch of stuff in this compiler. I don't want to, yeah, this compiler, I want this compiler to be simple. Okay, so all we're going to do is once we have this tree structure, we're just going to do a simple tree traversal algorithm. And whenever we see a node of a certain construct type, whether it's program, statement, list, or expression, we're just going to spit out, very systematically spit out an equivalent chunk of machine code. And to do that, we have just 3 tree walking functions to do that. So hopefully you can already see, and we'll see it when we program this, is that we actually have a pretty simple specification. Thus, by defining the syntax of the language, it actually gives us a really nice way to just focus on each individual construct one at a time, and we can design all of our APIs around that abstraction. So this is a sign of where having a different computation model. So instead of just saying, oh, I have to write this in C and I'm going to write a bunch of switch statements and if statements, if we think about this as a tree structure, and then we can just use recursion to implement this problem and not actually have to worry about, well, okay, pointers and RAM and just random access memory. We don't have to think in, if we don't think in that machine model, and we think in terms of this tree and recursion, then we can actually have an easier time writing this compiler. Okay, so in assembly code, these are the operations we're going to use. I'll go into this when I actually code this, but this is more for you when you actually want to write this. All right. Okay, who would like to take a break? I'm okay continuing. All right, let's do, okay, so people need a break. So I'm just gonna have to do this when live coding. Okay, so yeah, let's do a 5-minute break and then come back. So we'll have a good chunk of time to do the coding, because I feel like I'm always behind. So let's do a 5-minute break. Let's reconvene at 11:21, and then we'll actually code this thing out. All right, guys. I realized that I forgot to put my camera on. for those who are here, can you actually see my camera? Okay, yeah, I forgot to turn it on. Sorry about that. Ah, okay. Somebody asked, yeah, caret represents control. M represents alt. I think it stands for modifier or something, but M is the alt. You hold down alt. Alt minus. Oh, okay. Oh, MU. This is for passing, well, in Emacs at least, this pass, I think this, oh, depends on what piece of software you're using. Yeah, hold down Alt and hit, hold down Alt and hit U if it says MU. Oh, so I should say for email, if you remember from the first class, my email inbox is pretty rough. So if you're asking something about the class and it's not something personal, please use Piazza to do that. We should have a much, I mean, as I think people who are using Piazza before can testify to, it's we try to answer pretty fast there. So if it's about like course stuff, like I need help with Vagrant or when is this thing due, it's better to ask on Piazza. Yeah, I guess there's a lot of automated emails too, and there's a lot of stuff that's coming to my inbox. Slides. Okay, so somebody asked about slides. So I don't actually post the slides. Instead, I post lecture notes. They're generated from the same file. So I just, yeah, it just makes it easy for me to make the notes and slides. But this, if you look at the course website and go to lectures and click on each day, you can, I just use the reveal.js for the slides. They're HTML. I mean, yeah. It's just a different HTML style, I think. But yeah, all of the content is here in the lecture notes. They're identical, and the lecture notes also have some of my speaker notes as well. So there's a little bit more. So somebody is still asking about hitting Alt, using Alt U. Just like in a programming language, the meaning of keyboard shortcuts depends on the application you're using. Oh, for Nano, okay. Okay, somebody pointed out it's 1122. Okay, thank you. All right, let's actually program this compiler. So there's going to be a lot of stuff to talk about. There's going to be a lot of stuff I'm going to cover. But I think, yeah, really go to lab today because there's going to be a lot of stuff about the details of this that I'm sure you'll have plenty of questions for. All right, first things first, let me create the GitHub project, which I actually need to start writing code. I want to do this to start writing code. Yeah, for using Vagrant, check the notes from last time. You just do Vagrant up and then Vagrant SSH. So I'm just going to go through accepting the repository so you guys can see this again. And I've got my Vagrant virtual machine up. Oh, fortunately, it actually came up. That's fantastic. So I'm in my virtual machine. I'm going to go to my shared directory here. And this says I'm good to go with my repository. So I'm going to use the SSH version here because I set up my key and everything. And I'm just going to copy this to create my repository. Whoops, that was stupid. Okay, so you can see me making mistakes here. So I actually need to make the directory for this. Let's call it toy compiler. Let me copy this code to create a new repository. Let's see if this actually works. Oh, permission denied. Yeah. I literally just had this working. Okay, well, I botched something. Unfortunately, my machine restarted. You don't have to have your GitHub account connected to Vagrant. This just makes it easier to push, to do pushes. What did I break? Okay, well, I messed something up. All right, so I'm not going to push to GitHub, but I'll go through all the commits and everything. When you do this yourself, you'll be able to use, you should be able to use git push for this. But yeah, if you have issues, go to lab, and I'll fix this up. And if there's any particular issue for Vagrant, which I hope there isn't. Oh, actually, let me just check something real quick. So this will kind of go through how you set up this SSH key. So I added this SSH key today. And it's a different key for some reason. That's weird. Maybe it actually recreates my key. Well, now you can see how you actually add a key for your Vagrant box. So now you'll see, so remember, do your public key, not your private one. So now you have my public key. If you have a very fancy quantum machine, maybe you can figure out what my key is. Added my SSH key. Let's see if the fingerprint is the same. Looks the same. Can I push? That's weird. I don't have a passphrase. All right, I don't want to waste time on this. Sorry about that. So I won't be able to show you pushing and pulling, but I will show you doing the commits. And I mean, yeah, it's simple. Once you have everything committed, it should be fine. All right. Okay, so the first thing that we need in our toy compiler is our main. So the first thing that I like to do whenever I'm coding is to just write a hello world program, because I really like to have something that actually runs. Oh, can I make it bigger? Yes, I will make it bigger. How's that? Oh, this is Emacs, but you can use whatever editor you like. So just use whatever editor you like. Edit it in the folder. Yeah, I talked about this like a couple weeks ago when I named this file main.c. So this is just main.c. And now I'm going to create a Makefile for this to build it. And so go to lab to learn a little bit more about these Makefiles. But I'm just going to show it to you and just do it. So what a Makefile does is it automatically compiles. It's basically a kind of fancy script for building your, oh yeah, sorry. It's basically a fancy script for compiling your project. And it's kind of like a little domain-specific language where we can define variables. So here I'm defining what the source files are. These are what the object files are by just replacing .c with .o, and what the end program name is. You know, I don't have to go into such detail. I don't have to go into such. I don't have to make it so programmatic where everything's a variable. But I just want to kind of show you what. Because you'll encounter these if you do any homebrew or systems programming, you'll encounter these Makefiles a lot. So I just want to kind of get used to the syntax. Yeah, I'll give you a template. I'll give you a template for this compiler. But for now, you can just sort of copy what I have here. Okay, so what this is saying is, in order to build my program, which is called toy, I need to first build the object files, which is main.o. And so in order to build the program, I need to run the C compiler. So these money signs are just variables, and so they expand to the C compiler. I need to run the C compiler. I want to output whatever the program name is and use the C files to compile it. So this is just running GCC. And when I run this, you'll see what the actual commands turn out to be. So don't worry too much about the details of this. This is something that you can just copy. So one important gotcha here is that this is a tab. This is not two spaces. Makefile requires this to be a tab. This is something that, yeah, a lot of people, that this causes a lot of trouble for people writing Makefiles. But basically just copy this for now. In lab, he'll go over a little bit more about what the meaning of this language is. So no soft tabs. This has to be an actual tab. You would have this in a file called Makefile. So all right. So let me show my terminal now and show you what I have right now in my repository. So I've got this Makefile here, which defines how the program will be built. So all it's going to do is compile main. And of course, it doesn't work. What did I do wrong? So yeah, of course this is going wrong. Okay, I'm just going to copy the one that I already have and remove the other units. Okay, so I had some typo in there. So if you're having trouble with this, I'll just give you the Makefile. A Makefile is a Makefile type. So if you're having trouble copying this and you're getting problems, I'll just give you the Makefile. I'll give it out to you. All right, so we've got this Makefile here, which I made apparently some minor typo. So if you're having trouble, I'll just send you the Makefile. I don't want you to have to struggle like I just did. And we've got a main method. So basically, for this Makefile, just think that if I put new source files here, then it's going to build and link them for me. I don't have time to go into the details of how this works, but yeah. So just realize it's basically like a very fancy bash script for compiling and linking your program. So create a new directory for your toy compiler like I did, and you'll connect it to GitHub by how I talked about a couple of weeks ago. So use the same stuff that you used for GitHub. So Makefiles don't need extensions. By default, if you have something called capital Makefile and you run the make command, it will look for well-known Makefile names. Okay, so we've got our main. It's compiling to a program called toy because of our Makefile. So don't worry too much about how it works, but basically I named the output program toy, and these are the input source files. So yeah, don't get too hung up on the Makefile stuff. I'll just, so if enough people are having trouble with it, ask me and I'll just send the Makefile. I was hoping to go into more details about it, but I think, yeah, for lack of time. You need the Makefile. So you need the Makefile for the project. So the Makefile for the project will look very similar to this. During this class, I mean, it'll currently, so if you're following along in coding, I don't expect everyone to completely follow along in coding because I'm going to go through it pretty fast. But this is something where you can go back and pause the class to hand code some of this stuff. So for the Makefile, I don't expect you to have to hand code it. Just send me, ask on Piazza and I'll send the code for this out. All right, so now we have a Makefile that automatically builds our toy compiler. So make clean will remove it so that we can rebuild it again. So this is just Makefile conventions. This is something just to kind of, it's like learning a language. You just learn by seeing it being used and learn by using it. So you can see here that what the Makefile translated into were basically bash commands. We're basically running programs. So this ran the C compiler -C on main.c and ran the C compiler to do linking, outputting the toy program and taking in the object file that was created before. So does anyone have questions about these commands? These I think you should be familiar with, right? Does anybody have questions about what these commands look like? Okay, so you can see that all of this Makefile script that I did here, when we actually ran make, it executed the commands we need in order to compile and link our program. And make clean will destroy any compiled stuff. Yeah, I'll push it. So send me a reminder on like Piazza or something, and I'll put this Makefile in the lecture notes for today. Just because I didn't have time to go through even more detail. I'm already using a lot of time here. All right, so we've got our main now. I really like to get this stuff kind of set up as I go along, so I'm not having to worry about it while I'm doing coding. All right, so the first thing I want to do is program the Lexer. So recall from our slides that the Lexer is what takes each character from the input and turns it into tokens. Now, in order to have tokens, we need to actually define structures to. So somebody asked if they can send their Makefile. So you can send you can send the Makefile, but it may not handle the tabs correctly. But yeah, I'd send it there, but just be aware that if these here are not tabs, if this is not a tab, then the Makefile won't work. Yeah, so yeah, this is people are gonna have a hard time copying that from the chat. So for now, you could just run GCC for this. That's fine. You could just run GCC. You wouldn't have to do this. But for when you submit it, practice using the Makefile, because we're gonna need it for more than just running GCC later. All right, so I'm gonna make I'm gonna build the Lexer. So the first thing I'm gonna do is make the header file for the Lexer. And I'm gonna sort of just show by example how people use these header files. So for now, without going into the details of how they actually work, I'm just gonna make a header file, and in there I'm gonna put all of the definitions that I need for my Lexer. So this is just a convention to make sure that you're not including the same header multiple times. That's all this is doing. Yeah, this should be zoomed in. So I'm just going to include some standard libraries that I need. I need this for reading characters from files. I need this for checking whether something is a digit or not. And I need this so that I can exit with an error code. So I'm going to, so yeah, the Makefile should be in your source folder. So we make a new directory for your source code repository and then add that. So let me show a little bit of the structure. Let me show some of the Git stuff here. So once we have our files being created, just to make this a little easier to look at, and I'll give you all these files in the lecture notes. Okay, so by typing git status, it's going to tell us what files aren't currently in the repository. So to add them, all I have to do is say git add. So I'm going to add the Makefile and the git ignore file. Git ignore file just makes it so I don't have to look at all of the generated stuff, and the tilde files are just my backups from my editor. So, but I'll just put all this in the lecture notes, so you can just copy it. So now that I've added them, my git status now says that I've got these 3 new files. So git adds, so I think it's really dangerous to say stuff like git add dot or git commit all, because I want to have absolute control over exactly what goes into my repository. I don't want to be accidentally adding junk stuff that is either generated or stuff that is unfinished, stuff that is going to be bad for another contributor to have to deal with. So I think it's really good practice to be very specific about exactly what you're committing. It can be a little bit more laborious, but it makes for a cleaner code base, and it actually reduces steps, reduces problems for yourself in the future. Okay, so I'm going to use this git commit -p, which is a little bit tedious to use, but it also makes sure that you're very specifically adding only that code you really want to add to the repository. You don't want to break builds for other people. You don't want to add code that's, usually by convention, you don't want to add code that's generated or compiled to the repository. It's a source code repository. Okay, so now I've committed it, and it says I've only got these untracked files here. So these are just files that my editor creates. So now I've got this lexer.h, which I haven't finished yet. So one reason why I don't want to commit this yet is I haven't actually finished writing it. It's like partially done stuff. You can certainly commit partially done stuff, but it provides a nice check to make sure that you're actually committing what you really think is a change to the code, rather than something that's kind of in an in-between state between implemented and not finished. Okay. So just sort of follow along with that stuff. I don't have time to go into details. I would ask in lab about Git and Makefiles and running GCC. But for now, just kind of get muscle memory here for this stuff and get used to seeing it. Yeah, Git Commit P. So once you run Git Commit, it'll automatically open a text editor for you to write a command in. I also don't recommend using the -m flag for that. Just let it open the editor and really write take a conscious effort to write a sensible Git commit log. If you go work for a tech company like Google or Facebook, they'll be very, very happy with you if you're writing very sensible commit logs and being careful about committing code. Because if you can't demonstrate you can do that, they're not going to give you access to their repositories. Okay. So I'm going to use a type def here to define a pointer to a struct. So I think you guys should be familiar with structs and pointers, right? Is anyone not familiar with structs and pointers? Feel free to ask questions about it. Okay, so I'm going to make a structure for this token. And I'm going to use maybe a little bit of a trick that might be a little unfamiliar to some of you. I basically want this structure, a single struct, to represent all 4 of my tokens, but I don't want to have 4 different structures for that. Instead, I'm going to, because it's basically like having a single object. So in the same way that you can have objects in subclassing, we don't have objects in subclassing in C, so I'm going to use this little trick of having a struct that contains an enum and a union. And so let me write this out and explain a little bit so I'm getting some confused responses from people. So it'll become much clearer when we actually use this, but the idea behind this is a union is like a struct, except only one of the fields can be used at any one time. So while a struct has a data structure that has all the fields, a union is a data structure where you can choose between one of the 2 fields. So if you want to have something like subclassing from object-oriented programming, you can simulate that using a union. That has a number in it, can have a token that has a number in it, or a token that has a character in it. All of these structs and data structure definitions, they're all kind of schemas to define what your data looks like. So for a token, we want our token to be one of 4 things. And so one of those 4 things it is, and the union actually holds the data that represents the value of that token. Oh man. It's exactly like enum in Java. This is where Java got it from. So just think of this, it'll become clear as we use it, but this is basically saying I want a data structure that can be one of 4 different things. It can be one of these 4 kinds of tokens. And those tokens have different data being stored. So I use a union to describe that I'm going to have one of these different types of data for each of these tokens. So it'll become clear when I use it. Yeah, any object-oriented language allows you to do this using some here that has 2 fields, kind. Oh man, it has to go wrong. It has to go wrong now. So hopefully the recording should not cut out. The recording is going to be the recording. I hope. All right, so we need our Lexer, or we need our Lex function. So our Lex function takes whatever the file we're reading at the time and returns a token. For error handling, I'm going to define an error function, which is just going to terminate if we find that the input does not match our lexical specification. And then we need all of our are 4 functions that create tokens. So remember in the slides, I pointed out that in order to write our Lexer, we want to have a function that creates each token, one function to create each token. So it might seem a little tedious to do this now, but when we write our code, it's going to be much easier to have these helper functions around. So somebody asked a question about this type def. Why do we have it? Why do we have this T token instead of just saying struct S token star? It just makes it a little easier to write the program. We don't have to actually think too much about pointers. We can kind of hide pointers behind our type system. Let me actually code this Lexer, and hopefully it'll become a little clearer why we defined our API and our structs like this. Okay, here's our Lexer. This is our Lexer code. This is lexer.c. And by convention, we include, using quotes, we include the header, which has all of the definitions that we're going to use. So these are all the definitions. And this is our implementation of those definitions. So using this .c file, .header file convention, it makes it really clear where our specification is and where our implementation is. Oops. All right, let's start with the Lex function. So remember, the Lex function takes our input and produces tokens from that. So if you forget the specifics of pointers and stuff, and so one of the reasons why I'm trying to hide the pointers a little bit and hide it behind APIs is that we don't have to worry so much about pointer management. We can just, this is the whole game of specification versus implementation. By encapsulating that in a simple API, when we write our complicated algorithms, we can just forget about all that and just use the API that we developed. So I've created a very pretty small API here where we expose the Lex function and we use these create functions to implement Lex. So I'm going to kind of write the API for Lex, or write the implementation of Lex now, assuming that I've already written all the functions to create these tokens. So remember, the Lexer is what interfaces the actual raw file system and raw bytes of the files. It insulates that from the parser. So our Lexer is going to read characters from the input. Oh yeah, right. So yeah, the bottom has our file name. So sorry, it's a little small. Hopefully you can read it. Okay, so we're going to be reading one character at a time from input. That's what this statement does. And okay, so let me kind of like make this a little bit of a skeleton. There's a bunch of stuff we need to check here for these characters. We need to check, well, first of all, is it an EOF? Do we reach the end of the file? Did we see a number? Did we see a semicolon? Did we see an operator? And did we see something else? So one of the tips I tried to get across to you guys a couple weeks ago is, well, first of all, think about your specification first. And when you're coding, I actually do this while I code, where I'm like, well, I haven't implemented this, but I know what I need to implement. So I write in comments, here's what I need to do in comments. And I haven't fleshed it all out yet, but here's what I need to do in comments. The second thing is, if you have a condition, then always implement the else branch of that condition, even if there's nothing to do. Okay, so now I have like the kind of algorithm, it's kind of like this playing between pseudocode and real code. And so you can kind of write out the pseudocode first, or even just roughly in comments, and start filling it out. And that way, I don't remember things that much. So if I can just dump everything that's in my mind on the page, physically, even if it's in comments, then I don't have to worry about thinking that anymore. I can reason, well, okay, what are all the cases I need to look at? And these are all the cases I think that I need to have. So let's break this down a little bit more. Let's refine this a little more. So what do we mean by a number? Does anyone remember what we meant by a number in our language? What was our specification of a number? The ASCII symbol, right? The ASCII symbol. And what ASCII symbol do we need in order to know whether it's a number? Because remember, semicolon, operators, numbers, they're all ASCII symbols. So what's the ASCII we need for it? Is it any ASCII code? Are there specific ASCII codes? Yeah, we want the ASCII codes for 0 through 9. Now, there's a really convenient function in the C standard library called isDigit. So you can see that we did a little kind of refinement here where we had this high level idea we wanted. Okay, we're reading a character. We want to see if it's a number. When we go to implement it, we want to sort of gradually refine that into what the real implementation is going to be. So I know in some sense I need to use isDigit. But I haven't fully fleshed out this code yet. So for semicolon, it's something similar. For operator, it's going to be something similar. But let's start. Let me start implementing some of this stuff. So let's handle this EOF first. Standard IO defines this EOF here. So here's EOF. I check my character for it. Now the reason I check the reason that I do it like this, where I say EOF equals C instead of C equals EOF, is there's a really common problem in C where if I write something like this, these two are not the same thing, even though they look very, very, very similar. So this is one of the kind of gotchas in C. So a little kind of system programmer trick is you put the thing you're assigning to first in the comparison with double equals. And that way, if I'm saying something like, when I do isDigit here, so let me write out the isDigit. Oh no, never mind. That's different. But anyway, so EOF cannot be assigned to, I think. So if we were to accidentally say EOF equals C, we get a compiler error. So it's kind of a trick to allow the compiler to help us guard against this kind of easy mistake to make in C. Okay, so if it's an EOF character, so remember, what the Lexer checks each character of the input and returns a token. So if we see EOF, if we see that we're at the end of the file, what do we need to do? Return what? So we're definitely returning something. So return enum4, create an end token. Okay, good, all very good. So from our specification, we know that we want to return something. We want to return something here. We know that we want to, so let's put this in comments actually. So we want to return a token. Specifically, we want to return an end token. So now somebody was saying, oh, we want to return enum4. But remember, we can, instead of thinking about the actual data structure and having to worry about that, we can encapsulate that in a function. So that's why I created a function here called create end token. And so actually, when I was actually coding this, I was just like, well, I don't want to have to worry about creating that structure. So I'm just gonna, I'll actually write the function before I even implement it. I'll just write it and be like, well, okay, I know I have to do this at some point. And if I try to compile this, the compiler would yell at me and say, hey, you didn't implement this yet. So there's no way I can forget to implement it because the compiler is going to remind me. So this is what I think I need, right? I want to return something. I want to return this end token, but I'm going to like forget about how to actually do that for now. I'm going to pretend that I've already written that function. All right, so we've got some code that's kind of like reasonable now, right? Now remember, whenever you write an if statement, you always want to keep track of every condition here. So if I was being like really pedantic, I would put like an error message here and say, well, okay, remind myself, you forgot to implement this. That's if I was being really pedantic. But I think I can handle writing the whole Lexer function at once right now. So that's like one little trick. I'll show you that when I give you templates, I'm going to actually write some of that for you so that you'll have a nice, foolproof way to make sure that you're not having silent errors. So remember, the whole game is have the implementation always match the specification. And one way to do that is to just reduce the specification you're working on and make the computer, so this is like laziness, make the computer laziness and impatience. Don't make yourself have to think about where are the silent logic errors here. Make the computer tell you. So by adding else branches with explicit errors and by breaking things down into functions, even if they're not written yet, that way you don't have to remember whether it's implemented or not. The compiler and linker will just yell at you and remind you that you haven't implemented that yet. Okay, so let's check whether it's a number. So as I said, there's this isDigit function, and that's how we check whether something's a digit or not. And so what do we need to do if we see an ASCII code for a digit? So somebody said we need to do A to I. So, okay, and some others are saying create a number token. So this is hopefully, I think this is great here because I think I'm getting, this is a little bit of a teachable moment here. So one of the reasons programming seems so hard, particularly in C, is because it's very easy to think about all the details you have to do in order to implement that code. But one of the main things I want to get across to you here is that thinking about all that is not what makes you a great programmer. Even if you're the most, the smartest person in the world, I was about to say the most smartest person in the world, which clearly I'm not, you can actually do better than the smartest person in the world by using abstraction. Because no person that I know of can hold millions of lines of code in their head, yet people every day can work with multi-million line code bases, and they can build them. A single person can, I mean, it can take a lot of time, but you can build thousands and thousands. I mean, I've written code that's tens of thousands of lines long. And I do it not by thinking about the nitty gritty of the entire program, but I do it by abstracting away the details of the program. And so this took a little, working out the API, but I'm just gonna kind of give it to you that I know I have to create a number token. So I'm just gonna pretend I have a function written already called create number token. And there may be a little trial and error in place, but in order to actually figure out what the number is, I do need to run A to I on it eventually. But to do that, I'm going to need the character. So that's why this API takes the character. Okay, so what's the next token that we want to look at? So number token we did. Let's look at operator. Okay, so let's look at operator. Semi. Actually, let's look at semi because semicolon is how I coded it, and I want to make sure I didn't because I combined some of the error checking. So let's do semicolon next. So again, I use the same trick to make sure I'm not assigning C instead of testing it. And so what do we need to do what do we need to return if we see a semicolon? Yeah, we don't actually have to worry about how to actually do it, how to actually create the data structure. Let's just call a function and pretend like it's already written. Okay, so we've covered a lot of these cases. We've got semicolon here, we've got digit. So now we need to look at the operator. So the way I'm going to handle operator is with a switch statement, as somebody actually recommended at the beginning of the class. Let's use switch statements. So this is all pretty rote. So I'm going to so yeah, a lot of times when I use these C constructs, I kind of have a pattern in mind. Okay, so I have kind of a pattern in mind when I write these. And so without thinking about it, I'll just be like, well, let me write the structure of this. Let me write the structure of this thing. Let me make sure everything has a break statement. Let me make sure I have a default here. So without thinking about what I'm trying to implement, I think about the syntax of it. It's almost like this separation between syntax and semantics. And almost like what a compiler does. A compiler says, well, I have this construct and I'm going to pieces of it. Oh man. Wow, internet sucks today. Internet really sucks. So somebody asked, why is there a switch here? This is an API choice. So I've decided to make the create functions just handle the data structure stuff and have the Lexer function handle looking at individual characters. So you could certainly copy this code and put it in the creation function. You could totally do that, but the whole point of having specification and abstraction is that we make really well-defined tasks for each of our abstractions. And so my decision here, so you could totally do that. We could abstract it here by saying create an is operator function, but the is operator function is a switch statement. So we could totally do that. We could follow the same pattern of this is digit and say is operator and then pass it in. But I merged things a little bit. This is all kind of engineering and API design, and it's definitely not the one right way to do it. So yeah, we'll talk about projects in a couple of weeks. This I expect you to just copy. Okay, so here's our pattern for checking whether each thing is whether the next character is an operator. And so now it should be pretty clear by now what we need to do for each of these things. Oh yeah, actually the way I wrote this. So somebody asked about %. So is %, part of the toy compiler language? It's not part of our language. So you're thinking, what if I'm writing in C? No, if we go back and look at the specification, there's no % there. It's just addition, subtraction, multiplication, division. Okay, so I'm going to use a little kind of dirty trick here. Now, I recommend if you use this dirty trick in C, if you ever want to intentionally fall through case statements, that you put a comment there to remind yourself that, yeah, I meant to do this. There's actually a pretty serious security vulnerability caused by not putting a break statement in SSL certificate checking. It actually affected a bunch of Apple products and anything that used this particular library for SSL checking. Okay, so yeah, I haven't done the return part yet, but this is a little kind of dirty trick to say, is it any one of these 4 things? Then if it is, then create the operator token using that character. And now it turns out that you actually don't need a break statement if you're having a return. The switch statement, each of these cases should have some kind of jump statement, whether it's break or return. So this is kind of a little dirty C trick. If you're going to do this, make sure you explicitly say fall through. Yeah. Okay, so now another kind of little dirty trick here I did is because I put this switch statement in the else branch, that means this default actually handles every other token, every other character in this input. So that's why I designed it this way. So this way I can just handle my error here. Otherwise, I'd have to do a Lexer error in multiple places. So you could certainly write this in multiple ways. You could say, you could add extra else if blocks here to say, well, okay, if it's a plus, then create an operator token. There's many ways to write this. This is the way I happen to write this code, for better or worse. But that means that this default here actually covers all the possible characters. Which is what we want. We want to make sure that we're always handling every possible input. Every possible input here is covered by this default to a switch statement. Maybe a little dirty, maybe a little nasty, but you'll see in compilers and particularly systems code where there are legitimate cases where you want to fall through. I think this is a legitimate case. Others may disagree. Okay, so we had an operator and we had something else. I'm going to add a little, well, okay, let's forget about, well, yeah, I'm going to add a little, Yeah, so ORs, so yeah, the switches are equivalent. This switch is equivalent to ORs. So basically, we'll see this when we implement if statements and Boolean operations, that logical operators are equivalent to control flow. So an if statement is equivalent to a logical AND. We'll see that when we do backend code generation, but yes, this is equivalent to doing AND or. Okay, so to handle lines, remember, line breaks are done with a special character. So you don't need a break after the return because a return is, yeah, you don't need a break after the return because return, it'll be unreachable. Okay, so we need to handle line breaks as well. Because remember, our language says each line, or a language allows for new line characters. I didn't go into too much detail about this. It's kind of a particularly tedious part of compilers dealing with white space. The Lexer abstracts it all away, but I'm going to use another function called isSpace, which I think is defined in CSpace. So I'm just going to check if it's a space character, which means new line, space, tab. Then I'm going to do another kind of little trick here. I'm going to just call the Lexer again. So take a little, when you write this, take a little time to sort of think through why this works. Also, maybe a little bit of a dirty trick here. Yeah, a little bit of a dirty trick, but yeah. Some people are getting it. Some people are getting it. I wanted to make this really fast to write, so that's why I did it like this. All right, so this actually program is not compilable right now, unfortunately. So we have to do a little bit of work to get this into a compilable state. Yeah, isSpace picks up tabs. So let's just, actually for the sake of time, I'm just gonna copy these implementations. They're really boring, really rote. It's using malloc to do it. I'm gonna try to insulate you guys from having to use malloc in this class. I was hoping to type all this out, so sorry for not typing all this out, but you're gonna have all the code available to you at the end of this and in lab. So you can just hand copy this stuff. So let's just look through a couple of these. All I'm doing is using malloc to allocate a new token structure. And so you can see a little bit why I did a type def here. Because if I didn't do a type def, I would have had to say struct s token star all over the place here. So this way it sort of hides all the notion about in detail what the type of these tokens are. It's exposed a little bit here because we have to use malloc. But the idea here is I just allocate memory for this token. I set the kind of that token using our enum in the field. And that's it. So the end token is just a new token data structure where the kind is end. So so it may seem a little tedious to do this, but think about what it looked like when we wrote Lex. Our Lex function is really clean. And instead of having to worry about malloc all over the place, because a lot of students think like, oh man, I'm so dumb, or I can't program because all these pointers are really hard to deal with. Really, it's you're not being lazy enough. If you're being really lazy, you would have traded off that complexity with tedious, boring stuff. So I traded off all this malloc stuff by saying, well, I'm going to take the time to write an individual function for each one of these, so I don't have to worry about malloc anymore, because I can't reason about pointers beyond a few of them in my head. So I'm just going to like wrap all this and make a really clear API that says if I call create and token, I just get a new data structure magically. I don't care how it works. I just get it. So same thing with create number token. I create a new structure. I set its kind to be a number. And then, okay, so another little dirty trick here. I didn't use A to I. This is actually kind of what A to I does under the hood. Yeah, this is a little dirty trick that I'll leave as an exercise at home to see how this works. But this basically converts an ASCII code number to a machine integer. And I'll let you guys kind of, this is a well-known one that you can look up. You can Google it. So similar with the operator, I just create a new structure, set it to be an operator, and set the character. So you can see here that I can set both the character and the number of my token. And it's the same syntax as a struct, But union just says it can be one or the other. So you can't set both of them. And to know which one we're setting, we use this enum kind in order to distinguish when we use it, which one it is. It's kind of like poor man's subclassing. And finally, same thing for semicolon. So hopefully this makes the struct a little clearer. Hopefully it makes this, why this struct is designed this way, a little bit clearer, and why this API is designed this way. So the idea is Lex is what we expose from the Lexer. When I'm writing this algorithm, all I want to worry about is how do I process one character at a time? I don't want to have to care about creating these tokens. And then this token API, while looking like, why would you want to do this? Well, if we're writing Lex, we don't want to have to think about it. We don't want to have to think about pointers and malloc and structs, so I just wrap them all in API calls. Yeah, so somebody's asking, a very good question is, for some of these tokens, I'm not even setting the union. So I have a little bit of an implicit API here for, or I have an assumption here about how token is used. So because we don't have subclassing here and subtyping, the compiler is not going to check for us whether this union is set or not. So it's up to us to know that if we have this kind field, we always have to check the kind field. Whenever we use this token, we always have to check kind. And so that's an assumption that I make in this token field. There's not a great way to, the language is not going to help us do this. So we need to make an API that does this for us. So when we have, so I'm going to give you an API. So, okay, well, let's look at the parser, because we'll see that this assumption about how we use the data structure is going to be encapsulated in some API that we define for our parser for when we actually use these tokens. So yeah, so in C kind of necessitates some of these kind of complex assumptions that you need about your data structures, but we can use the function abstraction just to encapsulate that and encapsulate that all the way. And if you look at C++ and Java, they're really just language constructs that build in these kinds of APIs. So instead of having to write a function for everything, you can write a type that does this checking for you. Okay, let's look at our, okay, any questions about this Lexer so far? Because I want to move on to the parser. All right. So now I'm in parser.a. Oh, actually, we should be able to compile this now. Let me actually compile this. Okay, so I got an undefined reference to Lexer error. So see, here we got our my compiler, my linker is actually helping me make sure my specification is being implemented. So here's my Lexer error. I'm just going to copy it. It's just printing and exiting. That's all it's doing. And so you see how by just assuming that the API is written, that's actually, even though it feels weird to use code that hasn't written yet, it actually helps make sure that your specification is implemented. And already it's already working. So actually, let me real quick. Okay, for the sake of time, I'm not going to actually use it. So at this point, you could actually start running and testing your Lexer. So you could do unit tests on the Lexer itself. So you just run Lex in a loop, and you can actually print out the contents of it. But I'm not going to do that here. But just be aware that because we encapsulated this into the Lex function, in our main, we could already just start calling Lex right here. So I can call Lex once right now. And oh yeah. So it complains about this implicit definition. So in order to give the main access to the declaration of Lex, so this is not the implementation of it, the linker does that, but we're just including the header file. The header file just has the definitions. So now I spelled it wrong. So now it compiles. And now you can actually do your unit testing here, but I'm not going to do that right now. All right, so I'm in parser.h here. So here's my kind of boilerplate. This is the convention of how you write header files in C, and there are some really good reasons for this, but let's not worry about it. All right, so the parser depends on the Lexer to give it tokens. So we're gonna want to have access, we're gonna want to know about that Lexer API function. That's why I'm including lexer.h. And remember that our parser produces this syntax tree. And there were 3 constructs in our language. Do you guys remember what these constructs were in our language? I can go back to the slides to show this. So remember, the syntax of our language, yeah. So list of statements, statements, and expressions. So I'm just gonna make my kind of obligatory type test for these. I'm gonna assume that I've got these structs. So this is a good question. Somebody asked, why would you want to include standard IO here? Actually, this little if and def thing, this guards against multiple inclusion. And again, this is about encapsulation. So I'm thinking, what does parser need? Parser might need some standard IO stuff. So I'm not going to worry about what Lexer provides. I don't care. All I know is that Lexer gives me the Lex function. And I know that parser needs standard IO. I mean, they're equivalent. But but the idea here is really just try to break the problem down into, so you don't have to worry about what's encapsulated in Lexer. Okay, so here's my type defs for these 3 constructs. Let's see here. Okay, I think I have time to do this. So let me just write out some of these by hand so I can show you that it's not so bad. It's a little tedious, but it's not so bad. So remember, a statement list is really just basically a linked list where it contains a statement followed by some other statement list. So statement list, a linked list is really a degenerate tree. It's a tree that has a single child on each node. So our syntax tree is going to be very, very simple. Go to lab and Josh will talk a little bit more formally about syntax. But this is what our statement list construct looks like. It's a statement followed by another statement list. What is a statement construct, if you guys remember? Oh, another little gotcha here is that these struct definitions have semicolons after them because they're declarations. A statement is just something that contains an expression. So all this probably looks really, really like, why am I writing T expression? So again, this is about encapsulating each construct into its own structure and to kind of trade off the complexity of compilers with the tedium of defining your data structures very explicitly. So boring is way better than hard, in my opinion, especially when the end result is something that is kind of a complicated result. And remember, an expression is just 3 tokens: the first operand, the operator, and the second operand. You guys with me so far? Any questions on this? Pretty straightforward, right? And now we need our API, so all this is kind of tedious and boring definition stuff. So we want to have, just like the Lexer, we want to have a bunch of, oh, thank you, misspelling. And so again, these kind of misspellings, these are things that the compiler will check. So I'd rather have errors that are like things that can be automatically found. I'd rather have stupid errors like typos than errors like, how do I debug this pointer through 3 different C files and 10 different functions? Okay, so again, I'm misspelling stuff all over the place here. So this is our so just like Lexer, we had a bunch of internal, so this is like what the parser exposes. So the parser will tell the code generator, or the compiler will call the parser. And these are the functions that the parser is going to use to actually generate our syntax tree. And just like the Lexer had these create functions, we're going to have a bunch of functions here to create our abstract syntax tree nodes. So again, all kind of tedious API definition, but when we go to code our algorithm, I assure you that this will pay off to define all these. And when I was coding this myself, I didn't actually write all these out at once. I started coding the algorithm and then said, okay, what do I need? And then started defining the API. So there's a little back and forth between the specification and the implementation, the actual API specification. Okay, and to build an expression AST node, I need the 3 tokens. And as you'll see, if you take programming languages, you'll see a lot of type systems are designed around making writing this stuff a lot less tedious and a lot more automated. Okay, and so there's a couple of helper functions for using the Lexer that'll also define. And we'll see this when I start writing the algorithm. And of course, we need error handling. This is why I have standard IO here, because the error handling is going to use standard IO. Did I type operator twice? I totally did. All right, questions about this definition? So hopefully, even though, if you were to look, what is the difference between a statement and an expression? Yeah, so this is a good question. So this is really just about the language syntax design. I designed this so that a syntax is just an expression. You could certainly omit statement and just say a statement list is a list of expressions. You could do that in your abstract syntax tree. In the definition of our language, remember, a statement has a semicolon at the end, an expression doesn't. So a statement is an expression followed by a semicolon. This is really how abstract you want to get your syntax tree. So you've found a place where you could sort of reduce the number of nodes you have. But it can be, as we'll see when we implement the main project, it can be very convenient to make a nice clean mapping between the syntax and the abstract syntax. And we'll see that when we write our simple C compiler. Okay, here's our specification of the language. Now let's write our C program, or our implementation of this. So I'm going to add our C here to our Makefile, and I'll give you this Makefile at the end. So don't worry too much about trying to copy that. And let me show you the implementation. Okay. Let's write the parser stuff first. So let's include our API specification. And let's just start top down. Well, actually, to be really lazy here are the functions I want to implement, the parsing functions. So I'm just going to copy this in here. So this is a little dangerous because I have a bunch of empty functions here. So I need to be really careful that I am, yes, so typo stuff. So remember guys, this is things that the compiler will check. So this is why I'm I'm kind of sloppy with this stuff. So I try to be very precise about the stuff the compiler doesn't automate. But you'll see, I will make lots of typos, like all the time. Okay. So in order to do this parsing, this is going to look a little complicated. We need to get the tokens from the Lexer. And now for reasons that will become clear when we write this parser, instead of calling Lex, I actually want to hold on to that token so that I have to check that token multiple times. So if I call Lex, I don't want to lose the result from that token. And that'll become clear once we parse this. But the way I'm going to do this is I'm going to create a global variable. I know globals are seen as bad practice, but when you're writing compilers, writing one-off applications, it's okay to do this. You'll see this in system tools all the time. And so what I'm going to do is I'm going to abstract away calling Lex into a function that will call Lex, store the token, and I'll separate that from looking at the token. So I've separated the act of calling Lex and getting a token. I've broken it into two pieces. Calling next token to actually store that token, and calling get look ahead to inspect that token. Guys with me on this? So I've just decoupled decoupled calling Lex into two steps. Calling it and getting the return value, and actually using that return value. And we'll see in the parser why you have to do this, because there are cases where you want to look at the token without actually, and you might want to look at the token multiple times before you consume the next token. Okay. So let's look at how we want to parse our statement list. So I'm just gonna I'm going to give you a little bit of so some of the tedious parts of this is handling the end of file. This is kind of the less theoretical part. This you just kind of have to deal with. So my API for this is going to be if it's, yeah, exactly. So look ahead token is a way to safely store the token we get from Lex without losing it. So we can look at it multiple times. So that what should I talk about first? All right, I'll talk about what this stuff means when we actually use the parser in our compiler. Actually, maybe I should talk about that. Maybe I should talk about that now. So let's go a little top down. So in our main method, because we know that parse calls Lex, and we know that the parser returns an AST node, let's actually write what our top level main function, how it'll actually use this. So it's going to call the parse statement list, and it's going to save that result. So that result is going to be the syntax tree, the complete syntax tree. Now for some reasons, these are really engineering details, but the way I designed this was to, okay, so basically, in order to have that first token in memory, we need to call next token as the first thing we do in our compiler. So right now, when I define this, look ahead token is garbage data. So this is kind of a complex behavior between the main method and the parser. Yeah, just work through it in your head. But basically, we're starting at the beginning of the file without reading anything, and we kind of prime the look ahead token by calling next token, and then we can start parsing. Yeah, lots of mistakes here. Okay. Okay. After return, thank you. We've got really good Lexers in the audience here. Okay, so parse statement list. If I'm already at the end token, that means I have an empty file. There's nothing to do. There's no AST to create here. So I just return null. This is all just engineering details. But let's say we don't have an end token. We have something that's not the end token. So what do we want to do? What do we need to do if we're starting to parse the top of our programming, of our input program? What is a statement list composed of? What's the definition of a statement list? What's inside of a statement list? I think there's a little bit of a delay, so somebody's saying call Lex. So remember, I've abstracted away calling Lex into next token and get look ahead. So right now I'm on a token. I've already called Lex. I'm on a token. And somebody said a statement list is expression plus semicolon. So statement list. So let's look at our definition again. A statement list is a statement followed by another statement list. So it'll take a little bit to wrap your head around, but basically what we want to do is we want to recursively parse a statement and then recursively parse a statement list. And when we do that, we want to create and return a new statement list node. So somebody asking if we have a character here or a list of characters. The Lexer abstracts away characters from us. We have tokens at this point. So if you look at the type of this look ahead and look at the type of get look ahead, we have tokens. We've already abstracted away all the details of lexing. And now we're just dealing with a stream of tokens that we get by calling next token and get look ahead token. So I know I went over this a little quickly, the look ahead stuff. But okay, so this is kind of the pseudocode that we want. And let me actually just write out the pseudocode here for the sake of time. So a statement is, we want to parse a statement, or we want to parse an expression and parse a semicolon, then create a statement node. And here we want to just basically read operator 1, operand, operator 2, and then create an expression node. Does this kind of make a little more sense with this pseudocode here? Okay, so that's all we really want to do. So this is all parsing does, is it just defines this like basically, we'll see when we go into the theory of it, but we're basically just recursively traversing our syntax tree. That's basically what the parser is doing. It's basically just, it's kind of like, we'll see when we get to the theoretical side, but this is how we want to build this. So anyone that's still thinking in characters at this point, you're piercing the abstraction that we've created, and you're doing so in a way that will only confuse you more. So the whole point of having this abstraction, so I can't think about characters at this point. It's too confusing. So I think the best thing to do is to go to lab and walk through this carefully in lab. So, we've created this layer of abstraction away from the file and the characters so that Lex will just class in our compiler. I also definitely recommend rewatching this. The lab is recorded as well. Everything's recorded. The lectures and the labs. Okay, so let me go through and start implementing some of this. So the statement parser will parse a statement and then return an AST node. Similarly, so just like with the Lexer, we're assuming that the parser is already written. We're assuming that all of these parsing functions have already been written. And then when we want to implement something to parse the statement list, all we have to do is pretend like that function's already written and then just use it. Hopefully this is making a little bit more sense. I know there's some network issues here, but hopefully this kind of makes a little sense. We'll see this a lot more when we look at in a couple of weeks when we look at Simple C. But for now, just kind of copy this and get this into your muscle memory, the way this kind of parsing code looks. But just like merge sort, you're writing the merge sort function, assuming that merge sort is already written, so that you can reason about the algorithm on one iteration of the algorithm at a time. So similarly, parse our expression. So here's where we actually get the token from our look ahead. And now we don't, so this is checking that this is basically checking that the tokens are in the right order. So this will become a lot clearer when we look in detail at parsing in a couple of weeks. But basically, if our syntax tree has other trees as nodes, then we just recursively call those parse functions. If our syntax tree has tokens as children, if our specification has tokens as children, then we look at that token and just check whether it's the token we expect. We call next token. So once we've consumed this token, once we've seen the token that we expect to see, we can move on to the next token. Now I know this, so I know this part is going to be very confusing for people. So I think at this point, the best thing is to sort of copy this by hand and go to lab to get a more of a primer on syntax. And then in a couple weeks, when we look at the theoretical model of parsing, I think this will become a lot clearer. It's connection between syntax and recursion. But for now, just sort of get this into your muscle memory and marvel at how this works when we actually run this. For tracing code, I can, when we actually have to deal with this, I'll go through using a debugger to do this. But you can also just use print statements. Doing this with recursion is kind of a pain. It's kind of a pain to do this with recursion. But for now, it's really just making sure you've copied the code correctly. And as long as you've done that, as long as you're meticulous about that, then you shouldn't have too much trouble getting this written. So remember, you're not really being graded on whether your code like works properly. You're being graded on whether you are using GCC and Git properly. All right, so I'm gonna, for the sake of time, I'm gonna kind of go a little quickly here. I will put this up at the end so everyone can pause and look at the actual code. So I'm not trying to like trick you here. You don't have to write this algorithm yourself. You can use the algorithm we've written. Okay, so again, there's a bunch of kind of rote code to create the actual nodes. So just like with the token, we have just a bunch of nodes to fill out these data structures to call malloc on them. I know I'm going through this quickly. For detailed questions, ask in lab. I'm also going to be in office hours after this. But for the sake of time, I just want to get through this quickly so we can get to code generation. All right, we need our parser error. All right, so just to kind of review this really quickly, we decoupled calling Lex into saving the token and looking at the token. We wrote a parse function for each of our constructs, statement, list, statement, and parser. For each construct has underneath of it a bunch of children. The children are either other nodes or tokens themselves. So they're either other constructs or they're tokens. If it's a construct, if it's another construct that's a child, then we just recursively call the parse function. If it's a token that's a child, then we get the token from the Lexer and check whether it's the token we expect, check whether it's a semicolon. So for an expression, it's just 3 tokens, one after another. So we just get each of those and check whether it's the right token. And in order to create the AST, after we parse it, so each one of these just returns a new AST node. And the creation functions are just very rote functions. All they do is malloc the data structure and just populate each field of the data structure. That is it. So I know this is going to be really confusing right now. I know that. I know that this is going to be confusing. But look, that's why I just want you to sort of hand write the code. Yeah, the libraries, well, the libraries are to provide an abstraction, specification versus implementation. Okay, so hopefully my code should compile now and it should parse. And it does, amazingly. thanks to my audience Lexers. Okay, and now for the more amazing part of this, code generation. Now, I really, unfortunately, do not have time to go into the details of this, which really kind of sucks. I spent too much time at the beginning of the class doing this. So fortunately, the API for this okay, so it's a function called CodeGen. Let me set up the specification of this. So it depends on the parser. Actually, yeah, I guess it depends on the parser. So for each of these constructs, we have a separate function that generates code for that construct. So in the same way that for each language construct, we had a function to parse it. For the code generator, we have a function that generates code for it. So this is much simpler because there's no data structures to worry about. We're just using the parser's data structures. And we've got our, so this file is actually pretty short. I'm probably going to go a little bit over, but I know that's annoying to do, but it is being recorded. So if you need to leave or you want to leave, then class is officially over at 12:50. But I want to go over this a little bit more carefully. So I will go over by about 5 minutes. So just like before, I'm going to add my CodeGen C function, C program to my Makefile, and I'll provide these Makefiles. So don't worry about that. I'll provide the Makefiles. And for the definition of this, which is on the right here, there are these 3 functions that we need to implement. So in main here, so I'm in main right now, all I need to do is call GenCode statement list on this statement list that I got from the parser. You guys with me on that? With me on this? So we started with the first token. We call the parser, which calls the Lexer behind the scenes. For each construct, there is one function to parse that construct. They have this sort of complicated, but they have this sort of interrelationship between all the constructs. So the parser functions are recursive. We'll really do a deep dive on that in a couple of weeks, why that works that way. That returns a tree, a syntax tree. And then we just write a tree traversal algorithm that iterates over or traverses over each node of that tree and produces machine code. Just basically prints out machine code. And that's all that this compiler has to do. Okay, so so now let's actually write the implementation of this. So just using our same C convention for separating headers from specification and implementation. Let me be lazy here and take all the API calls that I want to implement. Okay. All right, the reasoning behind this hopefully will become clear when I write it. But basically, we know that statement list is a list. So to make this a little short to write, we know it's a linked list. So basically, we're going to write a linked list traversal function. So we could have written this as a true tree traversal, where we recursively called GenCode statement list, but I'm just going to write this as a linked list traversal algorithm. So as hopefully you're aware from CS1 or CS2, that linked lists, you can either traverse over them through a loop or you can traverse over them recursively. And there's some connections here between recursion and trees. and that notion of iteration versus recursion, because a linked list is really just a tree. It's a tree that where only every child has one, every node has one child. And so because of that, you can recurse over it. You can recursively traverse that list because it is a tree. It's just like recursing a tree. But I've chosen here in my implementation just to make this a little, I don't know why, I don't remember why I did this. This is just the way I did it. This is just a linked list tree traversal. Questions on this? Okay. So now this is all we have to do to traverse our statement list construct. To generate code for our statement, so as someone observed, a statement is just an expression. So there's nothing more we have to do besides recursively call code generation on this expression. Does somebody have questions on this function, on the gen code statement list function? It's just iterating over a linked list. And now the meat of our code generation is inside of the expression. The expression, remember the expression has all the tokens for our numbers and our operators. Okay, I'm just gonna write it, and I think it's much easier to see what's happening here than it is to explain. Yes, the code is just, well, we already have a tree that broke down the input into this hierarchical syntax. This is just iterating over that tree and generating whatever code is equivalent to the input language construct. So remember, the compiler is taking an input language. It's just ASCII code. If you try to run that on a machine, you're not going to get the results you expect. The ASCII code is defining a language that is completely made up. And it's this part of the compiler that is actually defining the meaning of that language. The parser is turning that language into a tree structure because that's like the first step of understanding a language is its syntax. And then the code generation is using that syntax tree to iterate over each construct of that language, of the input language, and spitting out equivalent machine code for that input language. So, okay, so this is gonna look a little bit gibberishy without having a good understanding of printf, without having a good understanding of how printf works. But let me go through this real quick. So all I'm doing is printing out tab. That's just for making the output look nice. So basically, whenever I see an expression, I'm going to output assembly code that moves the number of that expression, the immediate of that expression, into a register. So this is going to spit out, so if my operand was the number 1 in ASCII code, this is going to spit out move 1 to register A. That's the code that's going to be emitted. So remember, we're not writing assembly code. We're writing a program that generates assembly code. And we're basically making a template for that assembly code where we're filling in the pieces, like using the syntax, the text from our syntax tree or the information from our syntax tree. We're using that to fill in this template for our assembly code template. So %d, as you all know, I hope you know, outputs a number, and we get that number from the token that we lexed and that we put on our syntax tree. Questions on this? This is probably the most important thing to understand from this code generation function. If you can understand this, then I think if you can wrap your head around how we got from the ASCII code input to this line, then you've basically understood kind of the gestalt of compilers. You know, it's really just writing out the code that you're generating. So you're not writing the code that you're generating, you're writing a program that generates that code. So in some really simple sense, it's just a printf that's printing out that resulting code. There's a whole lot of detail and engineering that goes into that. Some people are getting it, some people need more sleep. But if you can get this line and see why this line works, I think you'll have a really good understanding of compilers in general. So you're reading in text and you're writing out text. And those texts, both of those text files happen to be specifications of programming languages. Okay, so some people are not getting it. Yeah, so writing this on your own. So I didn't write this on my own. I took a course on compilers. But if you can sort of wrap your head around this, so that's why I just want you to copy this code, just write it. Write this code and run it. And I think that'll make it a little clearer what this is doing. All right, so let me get the rest of this code in here so I don't go too far over class. Okay, so the first okay, so let me actually, to make this hopefully a little clearer, is recall our example code. Our example code, when it sees the ASCII code 1 plus 5, you don't have to have this done before labs. This is, you have 2 weeks to do this, I think, one or 2 weeks to do this. Okay, so remember, when we see 1 plus 5, the equivalent in assembly was to move the number 1, immediate 1, into register A, to move immediate 5 into register B, and to call add, and to run the add function. So remember, that's the equivalent of 1 plus 5. So in our compiler, if we see an input language that has the number 1 and if we see the input language, whatever the first operand is, we don't care what the operand is, as long as it's syntactically correct and we have a number there, we take whatever that number was. We take whatever that number was, which is held in this data structure that we spent a bunch of care building up. We take whatever it was and we just plug it into this assembly code. That's all we do. Make sense? So somebody's asking, isn't this only for register A? Yes, it is. And so we can, so if you want to worry about which register to choose, we can do that. But for this very simple exercise, I want to make the templates really, really simple, where there's only one thing to plug in. So for this template, all we do is plug in the operand. So similarly, for operand 2, we just want to always put that to register B. We'll get to register allocation. Don't worry, we'll get to that. That's definitely complicated stuff that compilers do. But for this very simple compiler, all we have to do is know that is because we captured some operand in our syntax tree, these 2 operands, we can just always take whatever that is, plug it into a template that says whatever that operand happened to be, generate some assembly code that moves that operand into register A. Whatever operand 2 is, take that, whatever it is, whatever the text of that is, and just plug it into a template that says move that into register B. And now, in order to choose between whatever operator we had from the input, here's our wonderful case statement again. So remember, always have your default, always cover every case. Here's my nice kind of mental compilation going on here. And now for each of these cases, all we need to do is spit out the assembly code to operate on those 2 registers. So you can see here, this is for add, it's always going to be add A plus B. For subtract, it's always going to be subtract A plus B. So okay, so yeah, this double percent sign is what printf you need for printf to escape the percent sign. For this, for multiply, it's just multiply. Now divide is a little bit more involved. There are some details of of the Intel ISA, which I'm not going to get into here. It's in the notes. But this is how you do divide in Intel assembly. It's just the way it works. It assumes that EAX already has your operand. This is, MIPS's reduced instruction set. This is CISC, very complicated instruction set. And then I just have some template code to call printf. And so this, I mean, you don't really even have to understand this. This is just template code. And hopefully I can finish this before 1. So, okay, so that's really it. Our syntax tree captures all of the details about the input language that we need. We pick out pieces of that input language and plug it into a little template that has the output code that we want. And we just print that out. We just print it out. Those templates should be. But for this compiler, the only kind of parameterizable parts are what the arguments to move are and which operation to output. The rest of it is just template code. Yeah, I'm gonna go over, at the end of this, for the recording, I'm just gonna like show each program here. But before I end, I wanna try to end, before 10 minutes. So let's see what errors I have here. So do I mean, who's asking me this? Main is asking. So main is complaining, so I didn't include the header for, thank God it worked. Okay, so where's my example? Oops. All right, here's my example code. Let's see if this actually works. There's my example. Let me pass it into my toy compiler and voila, we've got assembly code being printed out. So you can see this is the exact assembly that we wanted from our example here. Oops, that's, okay, sorry, that is, sorry. Okay, so you can see that the code that we got out from our compiler is exactly the code that we got in our output. I'm running the Makefile from Vagrant. I'm running all this from Vagrant. And now for those of you who actually want to stick around and see this, if you want to get this to actually run, then we need more assembly to get this to run. We need a main method. And I've given you some template code here. But what I'm going to do is show you, so I've written this in the notes so you can see it. I'm using some kind of Unix program environment tricks to do this. But basically what I'm going to do is I'm going to use cat to help me do this. This is going to be a little bit of assembly magic here. I'm sorry, command line magic here. All I'm doing is I want to print out the start and end assembly template, and I also want to print out the output of my compiler. Yeah, this is going to be, all of this is going to be recorded. So please, I'm over time, so all of this is recorded. All this is going to be recorded. So this little magic here is going to glue the template end and start with the output of my compiler. So here you can see I'm running my compiler here. So here's my output, example.s. There's my output program. And now I can just use GCC to compile it and run it. And I get each of the computation being computed and printed. Okay, so sorry for going over. I really need to work on time. I think a really good way to do this is to leave questions for lab. So I noticed somebody said they both understand compilers more and also understand them worse. So that's actually, I think that might be a good sign. So Socrates, I think it was Socrates said, the more you know, the more you know you don't know. So this is why I really wanted to do, oh yeah, that's right, my computer crashed. That's a good point. Thanks for reminding me of that. Yeah, so this is to make up for the internet issue I had. Said, okay, so I feel a little less bad about this. But yeah, Socrates pointed out, I think it was Socrates, the more you know you don't know. And so, okay, so one of the reasons why I wanted to do this simple compiler was to really drive home the kind of essence of what compilers do. And really the essence is just reading in text and printing out text that is equivalent code. It's printing out code. That's the kind of beautiful, cool part of this. Okay, it's Aristotle. Sorry, wasn't he one of our? I guess he was Plato's. Was he Plato's student or Socrates' student? Anyway, same line of thinkers, similar line of thinkers. But yeah, the more you know, the more you know you don't know. But yeah, so now that you've seen really the kind of essence of what a compiler does, is really just reading in text and then plugging in some of that text into a template for your output source code. And let me actually make sure. So I went over, so I'm only over by a few minutes now. So whoever needs to go, please go. I'm just gonna kind of wrap up and rerun stuff. I wanna make sure that the compiler that I actually wrote was working properly before I show it to you. So I'm also gonna show all the text on the screen. So when you, the Git stuff. Yeah, I forgot to do Git. Yeah, the Git stuff is gonna be important. Yeah, for now, just use Git add and Git commit. But I've put some of the instructions in the class notes as well. So I'm just gonna rerun again on the compiler that I wrote. You can attend any lab you like, either lab you like. So yeah, go to lab, and you can also ask how these command line instructions work. Ooh, I broke something. Let me put the complete code generation here. What did I break? Oh, I forgot the commas. Okay. Yeah. Now it's working. All right, everyone, have a good day. I'm just gonna put up all of the code on the screen so you guys can see it for when you write your project. I'm gonna start with the Makefile. I'll put that Makefile in the lecture notes as well.
And then in a week or two, we're just expected to have like traced the code and like hand typed it. We're not expected to be able to like write this from scratch.
No. You definitely do not have to write this from scratch. You can just take the code that I wrote. All I want you to do is just hand copy that code that I wrote on the screen. That's it. There's no,
Okay.
You don't have to like write it from scratch. I mean, if you want to challenge yourself, by all means, but I'm just giving you the code, and all I want you to do is hand write it and get it to like compile and run it and submit it via GitHub. That's it. That's all you have to do. I think this is laid out in, I put the assignment on web courses already, but that's all you have to do. Yeah, you do not need to write this from scratch at all. You shouldn't, I mean, it's C code, and if you know C, you should be able to read through it and trace what's going on for an input. But it'll be much easier to understand once we go into the theory behind how parser front ends and back ends work. Yeah, you don't have to understand the theory yet. Yeah, I kind of believe in showing you an example, and then that theory will have a little bit more context when we see it. So hopefully you can go back and be like, oh, that's why the parser is written that way, or that's why, you know, the code generation works that way. So that's my hope. So yeah, if you're confused, that's okay. Just handwrite the code, get some muscle memory, and practice using GCC and Git. Visit the recording to see them. I guess screenshots. I guess I could do screenshots. Let me see. So right now, think of the recording as the standard for it. Where's my good example?
Thank you, Professor.
You're welcome. Yeah, everyone is free to go. I'm just gonna stick around here to put the code up in the recording, and I'll be at office hours soon.
Cool. Have a nice weekend. Thank you.
Hey, you too. Take care. Okay, here is the Makefile. This will be in lecture notes as well. Here's main. Here is lexer.h. Lexer.c is a little large, so I'm going to scroll through it. Here's lexer.c. There's the end. Here's parser.h. Here's parser.c. There's the end of parser.c. Here's codegen.h. And here's codegen.c. That's it. So for editing the files, so remember, the Vagrant Virtual Machine provides a folder that is mapped both to your host OS and your guest OS. So revisit the lecture one to see how this works. But basically, inside of the Vagrant folder, this is my guest OS, or Vagrant, and the /Vagrant folder. All of these files are also in my host OS. As soon as Zoom is finished doing their encoding or whatever they do, I'll just click the button to have the cloud recordings available. So they should be available soon. I'll do a screenshot of the compiler as well and just put it in the lecture notes. I think that'll be easier. All right, everybody, I'm gonna move over to office hours on Gather. So if you have questions, come over. Yeah, thank you all. So sorry for making this a little bit of a rush. Yeah, thanks for the kind words. I know this is a little more rush than I'd hoped. All right, everybody. I'll screenshot all the files. Take care, everybody. Bye-bye.